Hello friends, welcome to the lecture of number theory. In number theory, we have studied earlier chapters as first was divisibility, then second we have studied primes and their distribution, third chapter we have studied congruences, and now we shall study the fourth chapter, which is Fermat's theorem. We are referring the book Elementary Number Theory by David M. Burton. Now this chapter is Fermat's theorem. Fermat was a French mathematician who lived in 17th century, and he has produced important results in number theory. Actually, he worked as a lawyer and magistrate, but because of interest in mathematics, he worked in his leisure time, but he produced the important results. Main results of Fermat is Fermat's little theorem and Fermat's last theorem. Fermat's last theorem is also known as Fermat's conjecture, and that remained unsettled up to more than 300 years, and then it is settled by Andrew Wiles in the year 1993. So he did the important work in number theory, and in this chapter we shall study mainly first as Fermat's theorem. The theorem statement I have written here. See, it is let P be a prime, and suppose P does not divide A. A we shall suppose positive integer. P does not divide A, then A to the power P minus 1 is congruent to 1 modulo P. So this we have to prove. Now we shall consider its proof. So we start with the proof. We shall start with taking first P minus 1 multiples of positive multiples of this integer A. We start with taking first P minus 1 positive multiples of A, that is the integers see 1 into A, that means A. P minus 1 positive multiples of A. 2 into A, that is 2A, 3A, and so on. The last will be P minus 1 times A. And we shall suppose this set of integers as 1. Now what we shall see here is these integers, no two integers are congruent to each other modulo P, and also none of them is congruent to 0 under modulo P. So we write no integers in 1, or no two integers in 1 are congruent. Congruent to each other modulo P. Congruent modulo P. And no integer in 1 is congruent modulo P to 0. Now we shall verify this. If this is not the case, if this is not true, so then we have, in the first case, no two integers in 1 are congruent modulo P. That actually we want to prove, but we shall suppose two integers of 1, distinct integers of 1 are congruent to each other modulo P. So then we have some RA is equal to SA, is congruent to SA modulo P. with 0 less than or equal to r is less than s is less than or equal to p minus 1. R and s are multiples of a and that are 1 to p minus 1. So r is between 0 to p minus 1, or it should be 1 to p minus 1, and s is also between 1 to p minus 1, and we assume r is less than s. So what this will imply, we see that p does not divide a, or GCD of a and p is 1. So therefore cancellation law holds here, and this implies r is congruent to s modulo p by cancellation law. By cancelling a, since p does not divide a, and thus this is not possible because r and s both are less than p minus 1, less than or equal to p minus 1, and therefore p will not divide the difference of r and s, but this is not possible. Since 1 is less than or equal to r is less than s and less than or equal to p minus 1. So for example, we may consider say a as, say p is equal to 5, we will consider, and a is equal to say 2. Then what will be this set? First p minus 1 multiples of a. That means it is 2, 1 into 2 is 2, 2 into 2 that is 4, 2 into 3, so multiples of we will consider, or we may consider 3 into 2 and 4 into 2. That is a, 2a, 3a, and last is p minus 1. P minus 1 means 4. And these integers, no two are congruent to each other modulo p, that we have stated here and that we have proved here. Now suppose we assume these two are congruent to each other. That means 2 into 2 is congruent to 3 into 2. Like this, r into a is congruent to s into a modulo p. Then this will imply modulo 5. So this will imply that after cancelling 2 is congruent to 3 modulo 5, and this is certainly not true, or this is not possible, and that is 5 does not divide 2 minus 3, and this is the contradiction, means this case does not arise. That is, no two integers are congruent to each other, and also no integer among 1 is congruent to 0. That what will happen if it is congruent to 0? Suppose Ra is congruent to 0 modulo p, then this will imply p divides r into a, but we have p does not divide a. Then if p does not divide a, then p must divide r. This implies p divides r, and this is not possible because r is less than less than or equal to p minus 1, or that means r is less than p, but r is less than p, therefore this is not possible, and this is the contradiction. So is not possible again. Thus no integer is congruent to 0, and no two integers are congruent to each other, that we have stated, and we have seen this as. Now further, so thus no two integer in 1 are congruent to each other modulo p. And now what further we will have, thus these integers in 1 are congruent to the integers 1, 2, 3 and so on up to p minus 1, taken in some order. Therefore the integers in 1 are congruent. Congruent modulo P to the integers. One, two. Because when we divide by P, the possible remainders are 1, 2 up to P minus 1. So 1, 2, 3 up to P minus 1. Taken in some order. So what is meaning of this? That means here exactly P minus 1 multiples of A are there. These are congruent to one of these, and in some order, or just we have considered the example as A was 2, P is 5 and A is 2. So what are the multiples of A? The first 4 multiples of A we have written 1 into 2, 2 into 2, 3 into 2, 4 into 2. And these numbers are congruent to 1, 2, 3, 4 in some order, modulo 5. Now we may refer that this is 2. 2 is congruent to 2 under modulo 5. And this is 4. 4 is congruent to 4 under modulo 5. This is 6. Now 6 is congruent to 1 under modulo 5. And this is 8. 8 is congruent to which number under modulo 5? That is 3. So thus this 2 is congruent to 2. This 4 is congruent to 4. This 6 is congruent to 1. And this 8 is congruent to 3. And thus this is the relation for congruence between these numbers, P minus 1 numbers, and these P minus 1 numbers. And now we shall multiply this, multiplying these congruences. Multiplying these congruences, we have, now see, the product of these two is congruent to the product of these numbers, and thus we have A into 2A into 3A and so on, into last is P minus 1 times A is congruent to 1 into 2 into 3 and so on up to P minus 1 modulo P. So this is the case we have. And now what is the left side? Left side, you see there are A. How many times A are there? P minus 1 A are there. And therefore A to the power P minus 1 will be there. And if we collect A together, then what remains? 1 into 2 into 3 up to P minus 1. And that is exactly P minus 1 factorial. So this is P minus 1 factorial. And what is the right side? Right side is again P minus 1 factorial under modulo P. So this is what we have. And you should understand how we have multiplied these numbers, that I shall consider again. For our example, we have A is 2 and P is 5. We have the set, this type of set for A is equal to P is 5, and we have 1 into 2, 2 into 2, 3 into 2, 4 into 2. This is set 1. And we have 1, 2, 3, 4, these numbers. And we should have the relation between these. So 1 into 2 is congruent to 2 under modulo 5. Similarly, 2 into 2 is congruent to 4 under modulo 5. 4 from this. 1 into 2 is congruent to 2, 2 into 2 is congruent to 4. Now 3 into 2 is congruent to which number? It is 6. And 6 is congruent to 1 under modulo 5. And further, the last is 4 into 2. 4 into 2 is congruent to 3 under modulo 5. So this type of congruences we shall have, and that we have written here. So the integers in 1 are congruent modulo p to the integers 1, 2, 3 up to p minus 1 taken in some order, not necessarily the serial order, that is a is congruent to 1, it may not happen. So this number actually here 2 is congruent to 2 here, not the first number. Similarly 4 is congruent to the last number 4 and so on. So taken in some order these congruences are there, and now we have multiplied these congruences. Now if you multiply these congruences, what we shall get? The left side multiplication is equal to the multiplication on right side. Now what is the left side multiplication? It is 1 into 2 etc. So we have written this a into 2a like this. This is the same product, and that this product will be 4 factorial into 2 power 4. So 2 power 4 into 4 factorial. And what is the right side? Again this is exactly 4 factorial. 1, 2, 3, 4. And product, that is 4 factorial under modulo 5. So this is the result we have obtained. A to the power p minus 1 into p minus 1 factorial is congruent to p minus 1 factorial under modulo p. Now what we can further do here for this congruence is p does not divide p minus 1 factorial, or the GCD of p minus 1 factorial and p is 1. So that is the condition for cancelling a factor from both side of congruence. So the GCD of these two must be the common factor and p modulo number, GCD must be 1, and here p certainly does not divide factorial of p minus 1, because this factorial of p minus 1 does not contain a factor p, and therefore we can cancel p minus 1 factorial. Now we can write, since p does not divide p minus 1 factorial of p minus 1, cancelling p minus 1 factorial from both sides. We get, now see what is remaining. If you cancel this factor, the left side remains a to the power p minus 1, and right side it remains 1 after cancelling p minus 1 factorial under modulo p. And this is the Fermat's theorem. A to the power p minus 1 congruent to 1 modulo p. Now here also you can see 4 factorial can be cancelled, because 5 does not divide 4 factorial. You see, because 4 factorial is 1 into 2 into 3 into 4, and 5 does not divide this number, and therefore this implies 2 to the power 4 is congruent to 1 modulo 5, where we have considered here as a is 2 and p is 5. So 2 to the power 4 means 5 minus 1, and thus the theorem is proved here. So this proves the Fermat's theorem. By taking particular example, we have also verified this. So this proves the theorem. And now we shall consider a corollary to this theorem. By taking any other example as p as prime which does not divide a, we can verify the Fermat's theorem. Now we shall state a corollary. If p is a prime, and a is an integer, or you may write then a to the power p. A to the power p is congruent to a modulo p for any integer or for all integer a. This result holds for all integers a. This result follows from the Fermat's theorem. So what Fermat's theorem says, a to the power p minus 1 is congruent to 1 modulo p, but there is a condition, p must not divide a. And p is a is an integer and p is prime. So there will be two possibilities, p divides a or p does not divide a. We consider the proof of this. First we shall suppose let p does not divide a and p is a prime. So therefore the Fermat's theorem is applicable. Then by Fermat's theorem, a to the power p minus 1 is congruent to 1 under modulo p, or that means p divides, here p divides the difference of these two, or thus if p does not divide a, then we have this as p divides, or in this case now we have, if p does not divide a, by application of Fermat's theorem, a to the power p minus 1 is congruent to 1 under modulo p. Now we can multiply both sides of this congruence by a. So multiplying both sides by a, we get a into a to the power p minus 1, that is a power p, and is congruent to a modulo p. There is no condition required for multiplication. We can multiply by any number on either side of the congruence, and thus the result here, hence the result. Now the second case is, next, if p divides a, then what will happen? If p divides a, then we have to prove the result corollary for both cases. P does not divide a and p divides a. Then p also divides a to the power a into a to the power p minus 1 minus 1. This is always true, because this a has p as a factor, and therefore p divides a into any number. And but what is this? This implies p divides, multiply by a, it is a to the power p minus a, or this implies a to the power p is congruent to a modulo p. By definition of congruence, when we say the two numbers are congruent if p divides difference of this, here p divides difference of these two, so therefore a to the power p is congruent to a. Thus in any case, either p does not divide a or p divides a, we have the same result, that is a to the power p is congruent to a modulo p holds, and thus this proves the corollary. Hence a to the power p is congruent to a modulo p for all a, for any integer a, and this proves the corollary. Now we shall consider some applications of Fermat's theorem, so where it can be applied. So applications of Fermat's theorem. First application we shall consider as to show that say 5 power 38 is congruent to 4 under modulo 11. This we shall consider. Now the computation, this number is bigger, so computation is not easy. So therefore, using the theorem, how can we prove this relation? And apparently we see what is p here, prime. What is the Fermat's theorem? Fermat's theorem is, if p is prime and p does not divide a, then a to the power p minus 1 is congruent to 1 modulo p. This is Fermat's theorem. And thus now here what should be a and what should be p, that we can observe. And by comparison we should see a should be 5 and p should be 11. So let a is equal to 5 and p is equal to 11. And certainly the condition holds, p does not divide a. That means 11 does not divide 5 and 11 does not divide 5. So therefore Fermat's theorem is applicable. and therefore by Fermat's theorem, what we can write by Fermat's theorem, a to the power p minus 1, a is 5, 5 to the power p minus 1 means 11 minus 1, that is 10, is congruent to 1 under modulo 11. So thus we have 5 power 10 is congruent to 1 under modulo 11. This we have obtained by Fermat's theorem, and we consider this as a starting result. We take this as starting point. Take this as our starting result. But you see what we want actually. We want to show 5 power 38 is congruent to which number, or that is 4, that we have to show. And but here we have obtained 5 power 10 is congruent to 1. Now we express 5 power 38 in terms of 5 power 10. Now 5 power 38 is congruent, we can write 5 power, actually it is equal, but equality, if you have the equal relation, then it is also congruent. So this can be written as 5 to the power 30. 30 I shall write 5 to the power 10 to the power 3 into 5 to the power 8. 5 to the power 8. See, 30 plus 8, 38 power is there. And further, but 5 to the power 10 is congruent to 1 under modulo 11. So therefore this can be replaced by, this bracket can be replaced by 1. 1 to the power 3 into 5 to the power 8, and that is again 5 to the power 8 can be written as, see, or we may consider reduce it in terms of 11, mod 11, or first we write this is 5 to the power 8 modulo 11. Further, 5 to the power 8 can be written as, this is congruent to, and we will continue 5 square to the power 4 modulo 11, and but 5 square is 25, and 25 is congruent to which number under modulo 11, that is 25 leaves remainder 3. See, 25 when we divide by 11, what is the remainder? So the quotient is 2 and the remainder is 3. So this is congruent to 3 power 4, and again 3 power 4 is say 81, and this is congruent to 81. We are reducing the numbers modulo 11. Further, you may observe here, that is 25 is congruent to 3 under modulo 11. The reason here. And therefore we have replaced this 25 by 3. Again 81, this is congruent to, so left side is 5 power 38, and we have obtained the result up to 81. We will continue it. 81 is congruent to which number under modulo 11. So we divide 81 by 11, and the quotient is 7, and the remainder is 4. So this is 4, and this is what we wanted to show. 5 to the power 38 is congruent to 4 under modulo 11. How Fermat's theorem helped to obtain this result, that we should note, and therefore this is the application of Fermat's theorem. Here, because P is 11, we should consider P as 11, and here base is 5, so we should consider A as 5. First apply the Fermat's theorem, we get the starting result is this one, and in using this result we express the required expression 5 to the power 38 in terms of 5 to the power 10, and adjust the indices or the powers, so the value remains the same, and each number is reduced under modulo 11. That means divide these numbers by 11 and replace it by the remainder obtained. So thus we get 5 to the power 38 is congruent to 4 under modulo 11. Now we consider the second application of Fermat's theorem. So Fermat's theorem can be used to show that a given number is not a prime. Now what is the converse of, what will be converse of Fermat's or contrapositive? Converse of Fermat's theorem is not true. That we will prove after this. But what is the equivalent statement of Fermat's theorem? So Fermat's theorem gives the corollary. What is the corollary? A power p is congruent to A modulo p. This we have proved. This corollary we have proved. And you see, if this does not, if p is prime, if p is prime, then A power p congruent to A modulo p. And so what if this does not happen? The contrapositive, the conditional p then q is equivalent to negation q then negation p. That means if this does not hold, A power p is not congruent to A for some integer A, then p is not a prime, or p is a composite number. So from Fermat's theorem can be used to show a given number is not a prime. N is not a prime means n will be a composite number. That is, if A power n is not congruent to A modulo n for some integer A, then n is not a prime. This is the equivalent form of corollary that we have considered, contrapositive. If this does not hold, then n is not a prime. For example, the integer, say 117, n is equal to 117, or that is 19 into 7 is not a prime. So it is actually 117. What will be the factors for this 117? 13, I think it is 13 into 9. You check it. 13 into 9. Yes. So 117 is 13 into 9 is not a prime. And to show this, we consider a smaller number A. To show this can be shown using the Fermat's theorem. It is not a prime. To prove this, or to show this, let A be a small number. Let A be small integer. Say A is equal to 2. Or to make the calculations easy, we consider A as smaller. So this does not hold, that we shall show. And now you see A is taken as 2. So what is n? N is 117. N is given to be, A is 2 and n is 117. That we have given, and we have to show that this congruence does not hold. So we shall have to show A power n. So to show, or we shall show 2 power 117 is not congruent to modulo 117. That we shall show. Now we shall see which powers of A are close to 117. What are the powers of 2? That first power is 2 only, second power of 2 is 4, third power of 2 is 8, fourth power is 16, fifth power is 32, sixth power is 64, and seventh power is 128. So this is little higher and close to 117. So we consider this is 2 to the power 7. Fifth, sixth, 7. We have 2 to the power 7 is equal to 128, and 128 is congruent to which number under modulo 117? That we should write. So 128 when divided by 117, the quotient is 1, and what is the remainder? So we have to subtract 117 from this, and it is 11. So 2 to the power 7 is congruent to 11 under modulo 117. But we want to show, we want to consider this power 117, and we shall consider this power 117 in terms of 7, because we have 2 to the power 7 is congruent to 11. And now we can write, or shall we use the Fermat's theorem here? But we don't know whether it is a prime or not, so we should not use the Fermat's theorem. And we will consider now 117. So 117 when divided by 7, 117 when divided by 7, we use division algorithm and see the quotient. The first term in the quotient is 1, and that gives the remainder here 4. And next number is 47. When we divide by 7, the quotient becomes 6, and the remainder is 5. So 16 is the quotient, remainder is 5, and that means 117 is equal to 7 into 16 plus 5, and therefore 2 to the power 117 will be equal to 2 to the power 7 to the power 16, like this, into 2 to the power 5 using this relation. The power is raised on both sides by this. This is 7 times 16 plus 5 using laws of indices. And again, this is further congruent to. This is congruent to, what is the 2 power 7? 2 power 7 is congruent to 11. So this will be 11 to the power 16 into 2 power 5 under modulo 170. Now again, 11 to the power 16 can be written as 11 square to the power 8. See, 2 into 8 is 16, and we write 2 power 5 as it is under modulo 70. We have to reduce the number. Again, 11 square is 121, and you see 121 is congruent to which number under modulo 117. So that is congruent to 121 power 8 into 2 power 5 modulo 117. And 121 when divided by 117 leaves remainder 4. So this is congruent to 4 to the power 8 into 2 to the power 5 under modulo 117, since 121 is congruent to 4 under modulo 117. And thus now we will write this again in powers of 2. 2 to the power, this is 4 power 8 is 2 power 16, 2 power 5 under modulo 117. And again, that is 2 power 7 is we know here. So this is 21, 16 plus 5, 2 power 21 under modulo 170. And 2 power 21 we write in terms of 2 power 7. 2 power 7 is we have known, and or we may refer this as 1, and this is modulo 2 power 7 raised to 3, or cube of 2 power 7. 7 into 3 is 21, modulo 170. And 2 power 7 is congruent to 11. So this is 11 cube under modulo 170. And again 11 cube is 11 square into 11 modulo 170. 11 square we have considered here, it is 121 and congruent to 4. So this is 4 into 11 modulo 170, or this is congruent to 44 modulo 170. And you see this is not congruent to 2. 24 is not congruent to 2 under modulo 170, or the left side is 2 to the power 170, and which have actually obtained as 44, and 44 is not congruent to 2 because the difference of this is 42 and 117 does not divide 42. So therefore this does not hold, this relation does not hold, and this shows that 117 is not a prime. Hence this is not a prime. Is not a prime. Actually it is a composite number. We have shown this is 13 into 9, and thus Fermat's theorem is useful to decide whether a number is prime or not. If this fails, then we can say certainly this number is not a prime. So this is the second application of Fermat's theorem. So thus we have studied Fermat's theorem, we have proved it, and we have proved the corollary also of Fermat's theorem, and then we have seen two applications of Fermat's theorem to show a certain number is whether prime or not. That can be decided by Fermat's theorem. So the remaining part we shall continue in the next lecture. Thank you.